Ladies and gentlemen, welcome on my e-learning class called Equilibrium of Materials. My name is George Kaptay from Hungary University of Miskolc, professor here, and I'm teaching my international students, and today I'm teaching to you how to construct one component phase diagrams. Doing it simple, using an Excel file and molar Gibbs energy functions. This is a homework actually for my students, and let me show how the homework looks like. So my students got an email with such a very simple file, and this is actually what they should first copy into their own homework. I prepared my homework, the first page, okay, it's called Homework number 1 by myself on Equilibria of Materials, and this is the title. I will select silicon as an element and let me copy the task. Okay, so what is the task? Each student has selected his or her own elements. Let me show them. Okay, so here are the students, here are the elements selected. Homework number 1 is done on the first selected element, and you see silicon is not in the list, and that is why myself, George, Professor George, selected silicon, not to do the homework for any of the students, but doing something similar, teaching them how to do it step by step. So that is why here it is silicon. Okay, so what are we going to do? We are going to construct this phase diagram below 100 bar, and I also set a point on this phase diagram at this temperature and this pressure, at which I'm asking my students to find in which state is the element. In my case it is silicon. And I also attached 3 files, one for standard Gibbs energies for solid liquid phases of Dinsdale, the second one the same for vapors after barin, and the third one is the list of standard phases for each element in the periodic table. By the way, let me show the part of this periodic table, and here I show to you that silicon is in diamond state, DIA, diamond, in standard state. Standard state means standard pressure of 1 bar and standard temperature of 298 Kelvin. In this simplified homework today, we don't take into account any of the allotropic transformations of the elements, we only take into account the standard states. Well, it would not be a problem for silicon, because silicon actually has this only solid crystalline phase, but for other students who selected other elements it could be much more difficult. But the goal today is not to make it difficult. The goal every day is to make it as simple as possible, but not simple. Okay, so silicon is selected, but before jumping into the actual homework, let me show to you some basics, and this basics is hopefully in this additional information file. So according to this picture, the engineer, meaning you, young engineers, should select the state parameters. This is the number of components, the list of those components, usually meaning elements, the mole fractions of those elements, the average mole fractions in the system, the value of temperature and the value of pressure, and in principle you can run experiments to find the equilibrium state, which is characterized by the number of phases, the names of those phases, the phase ratios and the compositions of those phases, which is the mole fraction of component I in each phase phi. However, this course called Equilibrium of Materials is not doing experiments. What are we doing? We are modeling and doing calculations through the Gibbs energy. And the basic principle is that the given system has the equilibrium phases if those equilibrium phases in the given combination provides the minimum for the molar Gibbs energy of the system. But this simple condition is sufficient only if you have a single phase. However, if you, for example, have two phases, alpha and beta, both contain the same components A and B in both phases, then you need an additional two conditions, one condition for each component. For example, component A in phase alpha should have the same partial molar Gibbs energy than in component B. And the same should be true for component B, and only then in the two-phase system you have real equilibrium. Today we talk only about a single component phase equilibrium. That is why everything simplifies. For example, see the number of components is 1. We select the given component A and consider only temperature and pressure state parameters, and we'll find only the number of phases and the name of those phases in equilibrium, and we will not find the composition of those phases. Why? Because the composition of this phase is pure A, because only pure A we have as a single component in the system. On the other hand, the phase fractions we are not able to find from theory, and this is good news because it means that the engineer can set the phase fractions in this one component state as he or she likes, and this is done by cooling or heating the two-phase system as the engineer likes, because upon heating, for example, the phase fraction of liquid is increasing on the expense of the phase fraction of the solid, and upon cooling, vice versa. In this case, we need only this equation for component A, and for the three phases, solid, liquid and gas, we have similar equations. For the molar Gibbs energy of component A in a solid state, we usually have three semi-empirical constants, A, B, C, as function of temperature, and below 100 bar of pressure, this quantity is not pressure dependent. Similarly, for component A in the liquid state, we have A, B, C, semi-empirical constants function of T, describing its molar Gibbs energy, and below 100 bar, it is not pressure dependent. Obviously, AL and AS are different semi-empirical parameters. For the gaseous or vapor phase, we have also similar three terms, but the pressure dependence is different. R is a universal gas constant, which equals 8.3145 joule per mole Kelvin. T is absolute temperature, P is a partial pressure of component A, and P0 is a standard pressure of 1 bar. Now for a triple point, these two Gibbs energies should be equal at the melting point, and from this equality you can find this equation, which is needed later to calculate the triple point. Let me show to you how the final result should look like. So this is your final phase diagram, what we are going to calculate today. On x-axis you see the temperature, on y-axis you see the logarithm of the pressure per standard pressure. Well, we actually will use the 10th base logarithm, but there is a small difference here. In the middle of the diagram you will have a triple point at which the solid, the liquid and the gaseous phases are in equilibrium. From the triple point up vertically goes the melting line, at which the solid and the liquid phases are in two-phase equilibrium. Left from the melting line you have a one-phase region of solid equilibrium state, and right from the melting line you have the one-phase region of the liquid equilibrium state. Similarly, you have the boiling line separating liquid and vapors, and you have the sublimation line separating solid and vapor phases, which we also call gaseous phases. So this is the task. Now for this task, we have to find first the molar Gibbs energies according to the general scheme. Okay? So first we need functions which describe as functions of temperature and pressure the molar Gibbs energies, and once we have those functions we will start the calculations. Now how to find those functions? Well, I can tell you, many people for long years have been working hard to find those functions for you, and now those functions are tabulated. So today we simply will copy those functions for different data banks and then perform the calculations. Okay, let's start from the data bank I sent to you. So this is a PDF file, the so-called SGTE data bank, composed by Ellen Dinsdale and published in the journal Calphad in 1991. You see, I am on page 133 of the total 174 pages of this PDF file, which says silicon. Well, it takes some time to find it. All the elements are in alphabetical order, so I don't want to waste time here. So you see, we have the diamond phase. You remember, in the periodic table, we already seen that diamond is really the equilibrium state of solid silicon under standard state. That's why we have diamond in the first place. And then we have a liquid state. I should mention that we have also other solid states. So these are the potential other solid states which we neglect today. So we will take into account only the first solid state you can find in this compilation and the liquid phase. So the first thing what I do, I copy this data into my Word file, so into my homework actually. So this is my homework file, you remember. So chapter 2 is called data. And of course you can write everything more difficult, but I am trying to be as short as possible. So this is the diamond phase. And then we have also the liquid phase. So let me also copy the data for the liquid phase. Here you are. These data are ready. But then we have also the gaseous state, which is actually the vapor phase. Now for this I sent to you another file, which is an Excel file. This is after the handbook of Barin, and from the handbook of Barin my students and myself, we created for you an easy file which has this generally valid equation. So I copy here. This equation contains A, B, C, D, etc. semi-empirical coefficients, which are given of course here. First I copy the first line, but I do it as an enhanced file, enhanced meta file, and then I copy the values. Sorry, I copy the values for the silicon. This is silicon here. Okay, copy paste silicon values. I go back to my homework and then again copy it as enhanced meta file, not to make a mistake. And this I put like this, that to make sure everything is more visible. Okay, so now I have everything, but of course using these equations by hand would take years of doing this homework, but we don't have years even in the times of the coronavirus. So I take an Excel file and copy everything into this Excel file. Okay, maybe I make it a little bit larger so you can see everything more properly on your screen, and I copy the equations like here, and of course I'm missing the last two lines, which I copy here. Okay, so this is not what I wanted, sorry for that. Let me rather copy from Excel to Excel, and then there will be no mistake. Right, so this is I, which you can see here. Okay, now I have all my equations. Now I have to calculate all these functions as function of temperature. So in column A, I put temperature measured in K. Let's look here. From these temperature intervals, one can see that we actually know these functions only between 298 Kelvin and at the highest of 3600 Kelvin. And that is why I start my table from 298. Let us go one by one, so step of 1 Kelvin, and roll it down till 3600. Take some time. Sorry for that, it's part of the business. Usually when you come to the point which you want, it will run further than you want. Okay, it's coming to 3000 and it's 3600 with us. Oops. Of course it's run further, but we never give up. Voila, 3600. Very good. So it was very difficult, so please save it. Now you can ask me a question. So ask me a question. Why you go only with the step of 1 Kelvin? Why don't you want to make a more precise result, calculate a more precise result like precision of 0.1 Kelvin or even a high precision of 0.01 Kelvin? Of course you can do that, but saying the truth, our current knowledge is simply not that good yet. So if we know the melting point or the normal boiling point of pure silicon with the accuracy of plus minus 1 Kelvin, then I tell you I am happy as a professor. We don't really know it better. So of course Excel can calculate anything you like, any precision you like, but it would be kind of cheating. Okay, the accuracy of our method today, Equilibrium of Materials today, which is called Calphad calculation of phase diagrams, is not that good yet, and that is why let us be happy with this step of 1 Kelvin. Alright, now first we write G silicon in diamond state unit joule per mole. Okay. And now the most difficult and boring part of this task is coming. You can make many mistakes. The more mistakes you take, the more days this homework will take. But I hope you will not make any errors in copying these functions into your equations. So let me show how not to make an error. So equals, I start with diamond, minus 8162 decimal point let me mention that in Hungarian Excel, decimal point is a decimal comma. This is what I am going to use. In your Excel, I have no idea what are the rules. Please study your Excel, how you should write everything, including the decimal point or the decimal comma. Okay? Plus 137, 23, 6839 times temperature. This is temperature. Oops, here. Minus 22.83 17533 times temperature times 11 temperature minus 1.9 12904 times 10 to the power of minus 3 times temperature times temperature minus 0.003552 10 to the power 10 minus 6 times temperature times temperature times temperature, meaning temperature cube, plus, okay, and this is a little bit missing, 10 to the power minus 1 is here, so plus 176,667 divided by the same A2, which is our temperature. Okay. And let me, by the way, move all these a little bit further so it will be more convenient later. Okay. So these are first value. Hope it is right. We will see it later if it's really right or not. If you click double here, then you have it at any temperature till the 3600 Kelvin. But this is not right, because as you see here, at higher temperatures the data bank contains a more accurate polynomial, which we really should use at and above 1687 Kelvin. So let me copy this equation there and go down to this temperature, 1678. Here you are. So I put my equation aside, and now, just in case, instead of replacing the old equation with the new equation immediately, let me put the new equation aside. Okay, so this equals minus 9457,642 plus 167.28 1367 times, of course, this temperature, this one, minus 27,196 times temperature times ln, same temperature, minus 420,369 times 10 to the power 28 times, and now its power, temperature power minus 9. In Hungarian it is hotvány. I hope you can use your Excel. So it's temperature to the power of minus 9. This is the value we got. And now celebration. Because the old equation and the new equation at the transition temperature, you see, provides the same values. And that means we didn't make any mistake. Congratulations. Of course you can say I could make a double mistake, but you know the chances that I make a double mistake which actually compensate each other exactly at the transition temperature, so those chances are so low that I believe this is the confirmation I have no mistakes. So now I erase the old equation, replace it by the new one. You know, Control C, Control V. There is a little green triangle here showing that starting from this line we start a new equation. Double click and now it's valid till the end of 3600 Kelvin. And now I can actually erase this not to confuse later my Excel. And now my second column is ready. So the second column is the molar Gibbs energy of pure silicon in diamond state in unit of joule per mole after Dinsdale copying actually these two equations. Next state is G silicon liquid in the same unit of joule per mole. Okay, Excel doesn't like G silicon capital silicon, doesn't matter, we are going on, equals. So now we are going to use this function. So this 42 533, 751 plus 107, 137, 42 times temperature minus 22, 831, 7533 times temperature times ln temperature minus 1.91, 2904 times 10 to the power minus 3 times t squared, which is t times t, minus 0.003552 exponential minus 6 times t times t times t plus brackets 176 667 divided by the temperature, and we have the last term, don't forget here, the second line, 209, 307 e minus 23 times, okay, the same function, temperature to the power of, so temperature to the power of 7. Correct? Correct. Equals. Okay, at the moment I am not sure if it's correct or not. There is one way to check if it's maybe correct, and the way is that we know that the melting point of silicon is much higher than the 298 Kelvin, and indeed the molar Gibbs energy of liquid silicon is much more positive at this temperature than the molar Gibbs energy of the solid silicon. So this is maybe probably true. So hopefully I didn't make a mistake. So double click and now it's calculated at all temperatures, but again please note we again have a second function at 1687 Kelvin. So let's go down again. Oops. 1687. Yeah, here you are. And here I am doing the same trick. But by the way, before doing the same trick, let me note something. These two values, so the molar Gibbs energy of solid and liquid silicon, at this particular temperature have the same values. It must mean that this is actually the melting point of silicon, which would be reasonable from Alan Dinsdale to make this special temperature at which he divides the two polynomials to make equal the melting point. How we can check that? So we can go back to the same handbook of Alan Dinsdale, okay, first page, and then not very far from the first page, sorry for that, what I'm doing now, we are coming to the table. Here you are, so you can see here the elements, the phases and the transition temperatures. And if we go down to Si, which is silicon, here you are, silicon is indeed a diamond. You remember we are working with the solid diamond phase. And look, this is the transition temperature, 1687 Kelvin, exactly the same as 1687 and 1687, at which the solid and the liquid have the same molar Gibbs energies. And let me show to you what I promised, that equilibrium between two states, solid and liquid, is when the same component A, silicon for my case, have the same molar Gibbs energies in two different states, solid and liquid. Okay, another confirmation that probably I have done so far a good job without making any error. Now to go on, I have to copy this equation aside, equals 403 70, 523 plus 137, 72298 times temperature minus 27, 196 times temperature times Ln temperature equals. And again, celebration, these two equal as they should equal at the transition temperature. So there are probably no mistakes in any of those data. So I erase the old equation, I replace it by the new equation, which is valid at higher temperatures. Again, I have this green triangle, I double click, and now I can erase the rest. So ladies and gentlemen, we are ready with solid and liquid silicon molar Gibbs energies, and now we should do the same for the gas, of course using the same unit of joule per mole. And again, Excel doesn't like capital silicon. Okay, probably we should shift those things a little bit closer again to make sure we see everything properly. So let me save it. Good. Gaseous vapor phase, this equation that I'm going to use. Parameter A for silicon I'm taking from here equals 446135 minus 46,0757 times temperature minus 18,4793 times, this is C, T ln T times T times ln T minus D, 0.00102 times temperature square, T times T, plus, we go to E, 3.2 times 10 to the power minus 8 times T cubed, T times F plus 6.2 10 to the power minus 13 times, okay, F 10 to the power 4, okay, T times, not plus, sorry, times T times T, okay, then the G is 0, Thank you so much. H has a negative value, so minus H in brackets 376 856 divided by temperature. You know H divided by temperature. Brackets closed, and finally I, which is 2.4 10 to the power 7 divided by brackets T times T, double brackets closed. Okay, I hope there is no errors here, but how can I know again? Well, I cannot really know, but at least I can compare to the liquid. Liquid at this temperature has 36,000 joule per mole, gas at this temperature has 399,000 joule per mole, meaning gas has a more positive molar Gibbs energy by more than 10 times than the liquid, which is reasonable because obviously we are very much below the normal boiling point of silicon. Okay, I double click again, and I am very happy to see that for the gas we don't play those games of several temperature intervals. Good. So I am kind of ready, at least kind of ready with introducing the data, and those data are also introduced into my Excel file. What I do next? Okay, what I do next, I remind you what is my task. My task is this phase diagram. The first thing, or the easiest thing to find, is the melting point. What is the melting point? Melting is the process when the solid transforms into liquid. Thus it has a special temperature at which silicon in solid state diamond must have the same molar Gibbs energy as silicon in the liquid state. Okay? So let me show it to you. I plot as function of temperature these two functions. Here you are. Okay, I am going to make it a little bit more beautiful. I put these, I remove this. Of course I need to mark temperature in Kelvin on x-axis, and I need to mark G, joule per mole, on the y-axis. And maybe I put temperature here. Maybe I put these legends up here, and then I can see my lines in a high resolution. For beauty I put it here. Very good. So what we can see, the blue line, you know, the diamond, this is the solid. Okay. Indeed, at low temperature silicon is in equilibrium in solid diamond state, and the liquid state, demonstrated by the orange line, has a more positive Gibbs energy, so liquid silicon at low temperatures is not an equilibrium state. But then there is a special temperature called melting point at which the two have the same molar Gibbs energies values. And if you go above the melting point, then the orange line shows more negative molar Gibbs energies, meaning at high temperatures liquid silicon is an equilibrium state and not solid silicon. The only thing is we have to find this cross section here. Well, if you keep your mouse long enough here, and if you are lucky, then maybe Excel will show to you this value. Oops, yeah, it showed to me something 1664, but you should understand that this is very much inaccurate. So what I do, in order to find a more accurate value, I create a new column, which is a difference between the molar Gibbs energy of the diamond state minus the liquid state. The unit is obviously the same. How I do it? Well, once we are at this point, it's very easy. I just take the B column minus the C column, double click here, and then scrolling down, and well, of course, first of all, I observe that these values are negative. Why they are negative? Because there is a difference of the negative solid minus the positive liquid. Of course, it is a large negative number, but then after the melting point, at the melting point it should be 0, after the melting point it should be positive. So I'm scrolling down and looking for the sign change. Okay, here I'm coming, and here I can see that indeed I have almost exactly the 0 difference between the molar Gibbs energy of the solid and the liquid, meaning that this temperature is the melting point. Congratulations. I hope you remember that this is what is given by Dinsdale, which is a confirmation that what we are doing so far is correct. So I am copying here, not copying, I am opening a new chapter, chapter 3. I call it melting point. Okay. And I say that the melting point of pure silicon is 1687 Kelvin. And as a confirmation, I am showing this diagram, which is up somewhere there. I am just copying this diagram here. Of course, as enhanced metal-fight, we have it more beautiful, and of course each diagram has a title. It's figure 1. This is the temperature, capital T, dependencies, sorry, of molar, I would say standard. Standard means pure silicon. Standard molar Gibbs energies of pure silicon in diamond state and in liquid state. And of course, from the cross section you can see approximately the value we found. Okay, so this diagram confirms that, and also blue line is solid, orange line is liquid. Great. Now let me go back to the task. So we found the melting point. Later I will be able to make a vertical line, which is called melting line, at exactly the same temperature. But this line terminates at the triple point pressure. So this is the triple point pressure here. Now I should find the triple point pressure. Fortunately, from my lectures, you know that the triple point pressure is calculated like this. Okay, over. Chapter number 4, triple point pressure. I provide the equation, just that the professor, who is me, understands where is it coming from. Okay, and then I use this, but I remind you that this simplified equation is based on the assumption that both functions contain only 3 temperature terms. In fact, they contain more temperature terms. So in fact, I take the difference between the standard molar Gibbs energy of the liquid silicon minus the standard molar Gibbs energy of the gaseous silicon at 1 bar pressure, divided by RTM, which is the melting point, and P0 is actually 1 bar. It just provides the proper unit of this transition pressure. So I should go down to the melting point. Remember, 1687. Here it is. Okay. Yes, it's true, because we have zero difference between solid and liquid Moore Gibbs energy, B minus C. But now I need the difference between the liquid, which is column C, I hope you remember, and the gas, which is column D. So this minus 202,007 joule per mole is the Moore Gibbs energy difference between the liquid and the gaseous standard state silicon at 1 bar. So I should divide it by RT times the melting point. Okay, and then I should take the inverse of the natural logarithm of this, which is exponential. In Hungarian Excel it is called kitevő. I'm sorry, in English Excel it is called differently, or in any Excel you are using, you should find it. The point is that this should be the inverse of the natural logarithm function. Okay? Here you are. This is the triple point pressure in bar. So let me copy it. Equals bar. Okay, very good. We also need the logarithm of that, or actually the ratio of P triple to P0, which is easy to find here, log 10 of this number, which is this number. Okay, triple point pressure is ready. Very good. Now let me see what is next. Okay, we have actually the triple point, and now what we should calculate the coordinates of the melting line, boiling line and sublimation line. But there is actually nothing to calculate at the melting line because it has a constant temperature. But we should actually calculate the boiling line. This is at higher pressures compared to the triple point pressure, and we should calculate some of the coordinates of some of the points along the sublimation line, which is at pressures below the triple point pressure. For that, so first the title, coordinates of sublimation line and boiling line, but this is not perfect, this title, coordinates of some points along the sublimation line and the boiling line. And now English is killed, so let me come back to the English language, American style. Very good, no misspelling, I'm happy. And to get this we need a table. So create a table. Here I put pressure, log pressure, and 1, 2, 3 different temperatures. Okay, so here pressure in bar, then log P divided by V0, then melting temperature in Kelvin, sublimation temperature in Kelvin, and boiling temperature in Kelvin. And now somewhere in the middle of this table I put what I found here. Like, let me put it here, and the log I put here. These are my starting points. At this pressure, I am sure that the melting point is 1687 Kelvin. You remember? 1687 Kelvin, melting point. Okay. Now, at this triple point pressure, the temperatures of all the three lines equal each other. That's why these three lines actually come together. Okay. So I can repeat 1687 and 1687 here. Right? Now then, let's increase and decrease this pressure in a meaningful way. So it will be 10 to the power minus 6, 10 to the power minus 5, 10 to the power minus 4, 10 to the power minus 3, 10 to the power minus 2, 0.1, and we need further lines. We need 1 bar, we need 10 bar, and we need 100 bar, because, so I should put probably here E to make sure what is the meaning. Okay, so the log is 2, 1, 0, minus 4, minus 2, minus 3, minus 4, minus 5, minus 6. Sorry, made a mistake here. And now we should also go to lower pressures, such as 1 to the power of 10 minus 7, which is minus 7. So this is capital E. And so this may be enough, or maybe I add one more point, because we will have sufficient number of points at low pressure along the sublimation line, and we will have sufficient number of points along this line. Maybe, okay, it doesn't matter. So I just want to see this table together. That's why I come here. Okay, now check again. Sublimation line exists below the triple point pressure. That is why sublimation line below the triple point pressure. Sublimation line doesn't exist at higher pressures. Melting point. Melting point exists only above the triple point pressure, not below. So, first of all, this is a constant. Independent of pressure, approximately of course, with the resolution of 1 Kelvin, but below, with the triple point pressure, there are no melting points. Now what about boiling? This is the boiling line. It exists only above the triple point pressure, not below. That is why here we put our crosses. And now what remains? It remains to find these values. Okay. First, let's talk about the sublimation line. What is the sublimation line? This is the equilibrium between the solid and the liquid. Sorry. Equilibrium between solid and the liquid. Sublimation line, solid and the gaseous state. So the mole Gibbs energy of the solid and the gas must equal at given pressure. At given pressure. So I must now add the new column P in bar. And the first question here is the temperature at log pressure -7. So I add here this value, and by the way I create the table also here. So it's sufficient to create it log P divided by P0, which is 2, 1, 0, minus 1, minus 2. Actually, we probably can go down like this. Now, instead of the, so here we should add the triple point pressure, which is this value, after 6. Okay. This is -7, -8, -9 and 10. Now this is melting point, which is easy, 1687. Remember, there is a constant value which is independent of pressure down to the triple point. This is the sublimation pressure. We don't have sublimation at high pressures, we have it only at the triple point, same sublimation point, and now we must fill these cells. How? First of all, we have to calculate the mole Gibbs energy of the gaseous phase as function of pressure. The first three terms are already written. They are valid at 1 bar of pressure. And now we have to add this term. Let's do it. So the G silicon gas at some pressure joule per mole silicon capital equals its standard value, okay, which we took from the baring data, plus the RTLMP R universal gas constant 8.3145 times the temperature times Lm P. Well, I should divide by P0, but P0 is 1, so that's why I don't care. Equals. Okay. In principle, this value should be lower than this one, and it is. Okay, good. So now I am looking for the equality of the solid and of the gaseous silicon at that pressure. The mole Gibbs energy should be equal, and then they are in equilibrium. And therefore I create a new column. G diamond minus G gas at pressure P. Joule per mole, of course. How I do it? Now it's easy, because diamond is given already here, minus, and this is the mole Gibbs energy of the gas at pressure P, and now I have this difference. By the way, before searching for 0, let me show on this diagram what is happening. On this diagram we have the blue line, which is the diamond, same now, and we have these as a liquid, but we can change it. We can make it gas. You see, now it changed, and actually we have a cross section. The cross section is somewhat above 1500 Kelvin, so this is actually the boiling point, sorry, the sublimation point, the sublimation temperature of pure silicon at this pressure. Now to find it more exactly, I'm scrolling down, searching for temperature when we see the change of the sign of this delta G, and indeed we find it somewhere here. So we can see minus 52 versus plus 225, and the question is which one is closer to 0. Now this one is closer to 0, that's why this is my sublimation temperature at the requested pressure of 10 to the power minus 7, exactly 1600. Let me also put it into my homework. Okay. Next, I do the same, changing the pressure. So now it's actually very easy. I just add one more 0 to this pressure. My orange line is shifted. Now the sublimation temperature is almost 1500. Let me search for this. Okay, here you are. So now we should select between minus 1.5 and plus 296, and obviously minus 1.5 is closer to 0, that's why the actual sublimation temperature is this one. Let me put it into my table. Okay, 1497, let me put it also here, 1497. You see, the trend is good, pressure is decreasing, temperature is decreasing as it should be. Next one, pretty the same, changing the pressure, adding one more 0. Is it okay? Did I add one more 0? No, I have done it. Now it is shifted. It's below 1500. Again, I am looking for the temperature at which the sign is changed. So now I have to select between minus 144 and plus 173. Well, this is a little bit better. I select this solution for myself. Put it into my table. 1406. 1406. Seems to be okay. Next, sublimation point by adding one more 0 here. Good. You see the orange line is shifted even more, so it's now around 1300 or something. Let me find it more exactly. Here you are somewhere. Now we have to select between minus 111 and plus 225. So minus 111 is closer to 0. I get this value. So this is my last calculated point along the sublimation line. Of course I can go further, but there is no much need. 1326. 1326. Right. So the coordinates of the sublimation line are ready. Now let me shift to the coordinates of the boiling line, which should start at 10 to the power minus 6. So change my pressure, removing many zeros, maybe 4, correct. But for that purpose I have to change the logic, because now I am talking about the boiling line that is between liquid and the gas. So the liquid and the gas must have the same molar Gibbs energy, the gas at given pressure. And that is why, okay, this is true for solid, this is true for gas. Okay, so now I change the solid to the liquid. Oops. And this cross section at approximately 1700 Kelvin should be the first boiling point. To find it more precisely, I need a new column, which must be the difference between the liquid and the gaseous. Molar gives energies at given pressure. Units are still joule per mole. Which can be easily calculated because C is for liquid, minus G is for gas at given pressure. Double click. I roll down to find more precisely the cross section of 1700 Kelvin or so. Okay, here we are. So minus 9.5 or plus 219, obviously this is closer to 0. This is our best boiling point at 1 microbar of pressure, and I put it also here. Next I should increase pressure. Good. So I remove 10 from pressure. Look at the blue line. No, sorry, orange line is shifted to the right. So now I have a higher boiling temperature. Let me find it more precisely. Not that far. Here you are. Minus 216 versus plus 22. Of course, plus 22 is closer to 0. So this temperature is our best value for the boiling point of this pressure. 1857. 1857. Okay. Next pressure. Easy. Just a little bit time consuming, but for the result he must push your limits. Okay, so this is already a little bit above 2000, you see. Let me check more precisely. Here you are. So now we should select between minus 111 and plus 78. Of course, plus 78 is a better choice, but I cannot see the temperature, so this is the temperature. We are going up, finding this value, putting it here. Maybe it's easier if I move a little bit this table. So it's 2072. Homework 2072. Very good. Next one, what about 1 millibar? So I change my pressure, removing 10. Orange line is shifted, something like 2300. Scrolling down, finding 0. Here you are. You should select between minus 124 and plus 45. Plus 45 is closer, so this temperature is our best boiling point for that 1 millibar of pressure. 2306. 2306 goes also into the homework. Next, remove 1 more 0 from pressure. Good. You see boiling point is shifted already to something like 2700. Go down. Here we are, more or less. And more exactly, here we are. We should select between minus 99 and plus 50, and plus 50 is closer. So these are solution, our best boiling point. Bed pressure 2601, 2601. Okay. Now we go to 0.1 bar. Removing one more zero. Orange line is shifted to further to the right. Boiling point is close to 3000. Let me check it. Yes. Select between minus 118 and plus 11. Of course, plus 11 is better. And this is our best boiling temperature at 0.1 bar of pressure. Sorry, 2984. 2984 I put into my homework. Next is 1 bar. This is actually the standard boiling point to be. Again, we have a shift here, so it's close to 3500. Close to the end of our table, I guess. Not yet. Okay. Select between minus 81 and plus 29. Of course, plus 29 is closer. The value is 3503. 3503. And now we should increase pressure to 10 bars. Okay, look what is happening to our graph. So this is the liquid. Okay, so this is not valid anymore. So this is the gas, and this is the liquid. There is no cross section anymore below 3600 Kelvin, which is the highest temperature. We have the data. So the conclusion is, in our homework, that we have no idea what is the boiling point. That it is not correct to extrapolate those Gibbs energy functions further than 3600, and that it is not correct to find boiling point above this temperature. Okay? So the table is ready. So chapter number 5 is ready, and now chapter number 6, phase diagram. Let me save everything in case of an accident. Alright. Now, let me show again, probably for the last time, how the diagram should look like. We have temperature on axis x, and we have logarithm of P over P0 along x, y. This is what we should do. Look here. Oh, by the way, sorry. This is a mistake I made, but now I'm correcting my own mistake. It is okay. You can correct your own mistake anytime. Even if my student is correcting my mistake, I think it over. If he or she is right, I am very happy. I give a plus point to the student. I never give a minus point. And then, of course, I correct my mistake. So that was a mistake because this was the boiling color. So what I want to say, that this form of the table is not particularly useful to make such a graph. So what I'm doing, I rather I reorganize the table to have a temperature table. So this will, the temperature column, this will be the x-axis, and right to it I put the pressure. So this is P for melting. So this is the same information, same two columns, just vice versa. But then I take again temperature here, and I put it below. Now this way I am doubling the melting point, which is no need. So, and I am copying this pressure, which corresponds to the sublimation process. And here I copy those values, and these are the pressures for the sublimation. And finally I copy the temperatures belonging to the boiling process, and I copy the pressures belonging to the same boiling process, and I call it P boiling. And now I have a nice suitable table to make a new diagram. So I plot as function of temperature the three different lot pressures. Oops, here you are. It is indeed similar to what we had before. Let me make it a little bit nicer. Obviously I need temperature in Kelvin, and here I need Lg P over P0. Let me move this to the top. Actually I don't need it at all. And let me a little bit work here. Minus 10, 2 plus 2. Okay, looks better. And this is somehow strange here. Okay, so this is what I calculated. Maybe it's a little error here, but let me not waste time now. But obviously in your real homeworks you should take care. Now to finish this phase diagram, I should explain who is who. So this is diamond phase here. Let me put it up here. This is the liquid phase. And this is the vapor phase. Okay, so solid diamond phase is stable left from the blue line, left from the orange line, here. Liquid phase is stable right from the blue line and up from the gray line. Obviously it goes on here, but we don't have data. And the vapor phase is stable down right from the gray and from the orange lines, here. We have a triple point, we have the vertical melting line, we have the boiling line, and the sublimation line. And I just put temperature here. These may be somewhat nicer. So now I can copy it to my homework, because this is my most important result today. Of course I copy it as enhanced Mattify, and this will be my figure 2, and the title is the Equilibrium phase diagram of pure silicon below 100 bar. Because of course it can be shown also at higher pressure, but this is what we don't do today. Okay, that's ready. And now let me remind you that we have a question, this kind of question. What is the equilibrium state at this temperature pressure? Let me copy the question and finally answer this in chapter 7 called Equilibrium state. Okay, 1100 Kelvin, 10 to the power minus 3 bar. Remember this. Come back here, put a new value here, 1100 temperature, and in the new column you put minus 3 as low pressure and end the point. How you do it? This is how we decide what we want to be on the diagram. Usually it's useful to copy this line, add a new line, copy it here, but remember the value is in column in line number 46, and this was only until 45, so I changed to 46. I put the same here, also change to 46, and remember that what I have here is in column V. So instead of R, we write V once, again, second time, V instead of R. Okay, okay. And now, well, now you cannot see anything, but there must be something here. Yes. Here you are. It wants to be a line, but it cannot be a line because it has a single point. So you have to format this point in a way that you don't want the line, rather you want the mark. So here you format your mark. Okay, ready. And you see? Here's your point, 1100 Kelvin, 10 to the power minus 3 of pressure. I copy it. I put it into my homework. Of course I have the title, which is similar to the title of figure 2. This time it's figure 3. The rectangular phase diameter pure silicon below 1 bar with a point in question. Very nice title. And now look here. You see the point in question is situated fully in the region when only one phase diamond, solid silicon, is in equilibrium, and this is what I am writing as a conclusion. At this temperature and this pressure, silicon is in equilibrium as solid, okay, diamond as a solid diamond crystal. See figure 3. From where it is obvious. Ladies and gentlemen, we have done it. The homework is ready, so now just let me check it again. We have a title, we have the order, we have the full title, we have the date, we have the task, we have the data, we have the melting point, we have the triple point pressure, we have the table with the coordinates of the melting point, sublimation points and boiling points, we have the phase diagram, and we have the equilibrium state for the point in question, and we have even the description explaining that the equilibrium is solid diamond for this point, and this was it. Because let's check again the task. Selected the element, calculated phase diagram below 100 bar, characterize its equilibrium state at this temperature and this pressure, answer the question how many and which phase are in equilibrium. Okay, how many phases? Well, not really answered, sorry. So at this temperature bar, silicon is in equilibrium as a single phase solid crystal. Okay, now I surely answered properly, and that's it. Okay, save again. Very good. Save as a PDF file. Okay, saved. Look if you have it. Yes, you have it. Check again if the PDF file contains what you want. Yes, yes, yes. And yes, yes, yes. And now I am happy. And now, ladies and gentlemen, it's nothing else to do. Just send your homework back to me by email and get your points. It might be you can find some mistake in this long lecture. If you really have found the mistake which I made, please write me an email. You have your extra point. Whatever you write, you can get a 0 point if there is no mistake, or a plus point if I really made a mistake. You will never have a minus point with me. See you the next time. Thanks a lot for your attention.